Hi everybody, this is an intro to the Quantopian lecture series, so if you're already familiar with Quantopian and with the lecture series, please feel free to skip ahead. Quantopian is a crowdsourced investment firm, and our goal is to democratize quantitative finance and to level Wall Street's playing field by providing a lot of free tools and data of the same caliber that you would run into as a professional on Wall Street. Our business model is to provide capital allocations to the best algorithms that are developed on the platform. To this end, we've developed a pretty extensive educational curriculum to make sure that our users are well educated. The Quantopian lectures are developed in conjunction with and are used for teaching by professors at top universities all around the world. We also work with industry practitioners to make sure that all the examples that we teach are current and up to date with techniques that are actually being practiced in the field today. In general, we try to teach theory and intuition hand in hand, so that once you've learned a concept, you have readily accessible code snippets to then go out and apply it. Let's get right into it then, and see what we're getting into today. So today we're going to talk about statistical moments, and more specifically, the skewness and kurtosis of distributions. These are two higher order moments akin to mean and variance that we can use to further describe how a probability distribution is distorted in space. A lot of times we just use mean and variance to describe a distribution, this central tendency, the mean, and how much it varies around it, the variance. But sometimes this isn't really enough to describe something, which is why we need to go to these higher order moments. If you have a probability distribution that has no skewness whatsoever, it looks kind of like this normal distribution here. It's symmetric around its mean. It doesn't have any weird forces pushing it in one direction or the other, right? Skewness is a measure of how skewed something is away from this symmetry. And a lot of times when we have a unimodal distribution, we can usually describe or infer whether something is going to be positively or negatively skewed based on where the mean and the median are in relation to the mode. So this is just for unimodal distributions. But generally, if the mean is higher than the median, which is then higher than the mode, we're going to have a positively skewed distribution. Whereas if we have a mean that is less than the median, which is less than the mode, then we're going to have a negatively skewed distribution. This is what these two different types of skewness look like after we calculate this higher order moment here. Recall that the mean is the sum of all these single things, just the average across the xi's, and the variance is the sum of the xi's minus their mean squared. This brings us up to this cubed polynomial here in order to compute the skewness. If we look at these two different ways that the log normal distribution can be distributed, we see that we have this positively skewed distribution here in blue, and this negatively skewed distribution here in green. And if you were to plot the mean and the median of each of these in conjunction with the mode, well, if we see the blue one, well, the mode's around here, the mean's probably going to be around here, and then the median will likely be there, splitting us between 50% and 50% of the data. Similarly, the mode for this green one's going to be around here, because that's just the maximum of the distribution. Then we're going to have the mean probably around here, followed by the median here or something. But generally, that's a good rule of thumb for unimodal distributions. If we start getting distributions that have many modes or multiple peaks, that rule of thumb is not going to be so helpful anymore. So these are continuous probability distributions. And it's not quite so obvious to see the skew from looking at a discrete set here. So if we pull SPY returns here from 2012 to 2015, well, they have this negative skew of negative 0.2, but we can't really see that easily on this discrete thing here. It's better to go with the computed skew rather than trying to get it from a graph. As in most cases, we generally want to rely on the actual statistical computation of some feature or another rather than relying on looking at pictures. So the next higher order moment that we're going to discuss is the kurtosis of a distribution. So the kurtosis of a distribution is the way that we measure the peak, or how peaked a distribution is. A normal distribution has a kurtosis of 3. So what we often do is we talk about the excess kurtosis. So the kurtosis that a distribution has in excess of the normal distribution, which is generally calculated by taking the kurtosis and subtracting 3. So if you have positive excess kurtosis, or some amount of kurtosis higher than the normal distribution, then we call that a leptokurtic distribution. And that's this blue guy here. It's more pointed and generally has fatter tails. This mesokurtic distribution has the excess kurtosis of the normal distribution. So it looks about the same as far as roundedness and as far as tails go. If we have a negative excess kurtosis, such as here, we call that a platykurtic distribution. And that ends with a slightly lower peak and less fat tails than the mesokurtic or the leptokurtic distributions. Each of these different shapes of distributions correspond to more frequent jumps away from the mean, or less frequent jumps away from the mean compared to the normal distribution. Because we see that stuff gets more concentrated in the center the more peaked we are, and we see that stuff gets less concentrated in the center the less peaked we are. We generally compute the kurtosis in a similar way to the skewness up above, and this is a fourth order polynomial. So this is the fourth moment. So as n approaches infinity, this form gives way to this form here. So we've been dealing with continuous distributions for the most part, besides that one sample from SPY. So this is the general form that we've been doing. If we want to actually directly compute the skew or the kurtosis, we can just do stats.kurtosis of the returns or of whatever time series or distribution that we think we have, or stats.skew in order to get the skewness. So you probably noticed that the kurtosis, at least in this form, looks particularly similar to the skewness up above, as well as the variance in general. And that's because these are these standardized moments. And all these standardized moments take the form of expected value of x minus the expected value of x raised to the kth power, or some kth power inside here, divided by sigma to the k, and that sigma is the standard deviation. So in this particular case, variance takes on the form of k equals 2, skewness takes on the form of k equals 3, and kurtosis takes on the form of k equals 4. This first standardized moment that we have is always going to be 0 because, well, we take the expected value of x minus the expected value of x. This turns into the expected value of x minus the expected value of the expected value of x, which becomes 0. So that just zeroes out. So all that we really care about is the second through the fourth moments. And these provide us just new ways or other ways to describe the distribution from just using the mean and the variance. Another way, or a classic way to test for normality, is using something called a Jarque Bera test. And what the Jarque Bera test does is its test statistics are based on the similarity of the distribution that you're trying to test to the normal distribution. So it looks at this skew, it looks at this kurtosis, and compares them to a normal distribution to see if your distribution that you're testing is normal or not, or likely normal or not. So the null hypothesis of this test is that our returns come from a normal distribution. So depending on our alpha value, I typically choose 0.05. If our p-value is less than 0.05, then we conclude that the data is non-normal. Whereas if our p-value is greater than 0.05, or what our alpha is, we conclude that our data is normal. Remember, we want to make sure that we're just looking at whether the p-value is above or below our chosen alpha, our chosen significance. We don't want to try to talk about relative degrees of normality. We're trying to come up with a definitive test. So we just want to treat it as binary. So all of our tests are written a little bit differently across various different programming languages. So you need to double check, at least in documentation. Like I know I just told you which side is the null hypothesis and which side is the alternative hypothesis, but it's good to check which is the correct side. So this is just a quick little sample of pulling that together. We generate n samples from a normal distribution, or n sets of m samples from a normal distribution, and we perform the Jarque Bera test on each one of them. And we're just going to look at the distribution of these p-values to see which ones pass and which ones fail, given that we know that all of this stuff that we're drawing is normal. So in this particular case, we see that the test is indeed calibrated properly. It's around 0.064 once we sum everything up and average it. So that's our number of significant tests. And that just means that we're wrong around 6% of the time here, which is exactly what we want. well, close to what we want. Since we chose a significance level of 0.05 that we've been talking about here, that 0.05 is going to equate to being wrong around 5% of the time. So this test is working exactly as expected, so that's good. So we can talk about our Jarque Bera test like this. So if the p-value is greater than 0.05, the returns are likely normal. Whereas if the p-value is less than or equal to 0.05, or just less than 0.05, the returns are likely non-normal. Yeah, and this has been just a general discussion of skewness and kurtosis and higher order moments. Hi everybody, thank you for watching the Quantopian lecture series. If you have a desire to see any more of our content, it is all available at www.quantopian.com/lectures. If you're already on the Quantopian site, you can also get to this page by going over to Learn and Support, clicking on Learn, and then this lectures link will bring you right back here. All of these lectures have a notebook associated with them, which contains the theory and applications for the lecture. It's the real meat. Many of these lectures will also have a video associated with them that you can watch, just like the one that you just watched. And then some of these lectures are going to have algorithms that you can clone and iterate on just to give you a basis to start with your own algorithmic trading ideas. We also have a GitHub, which is at github.com/quantopian/research_public. All the stuff that's on our lectures page is also here if you dig around. You can also follow me on Twitter at clean_utensils. And we also have, last but not least, some resources available for any sort of academics who want to incorporate the lecture series into their classes. All of this stuff is free. We just like to provide a little bit more guidance for professors who want to get Quantopian involved with how they teach. Lastly, you can email me at max@quantopian.com, and that's just max@quantopian.com. Feel free to send me any sort of feedback, any sort of questions you have about the lecture series. We're always looking to improve things, so we always want to hear comments about how we can make it better. Thank you so much.